Hi all, welcome to today's session. I am Jithin and today I will be introducing a cool and powerful tool or platform called Colab. We will see in detail about its features, benefits and how to migrate your work to GPUs and TPUs with a deep learning use case. Let's start. This will be the agenda for this section, in which we will be starting by giving an introduction to Colab, its features, functions and how to use them. Secondly, we will move on how to collaborate your works in team and sharing your projects with the world. Next, we will see how to migrate your projects and working with GPUs and TPUs in Colab. Here we will see the power of GPUs and TPUs that are provided for your project. Next, we will see different data processing and accessing methods, which includes how to access your cloud bucket data, data stored in your drives, and using BigQuery for processing and accessing large real-world data. Next, we will look into a deep learning use case. Here, I will introduce the machine learning pipeline and how a deep learning model is built, trained, and used for prediction. It's time to dive in. The first section will be an introduction to the Colab. Here, we will explore some of its features, how to code in Google Colab, and the functions like how to save, how to use the revision histories, then how to upload your notebooks and how to use them. So you may access the Colab notebook or the Google Colab repository just by typing the link colab.research.google.com. So once we have this link, we will be directed to the Colab space. So here we can see that there is having a 5 tabs where the recent tab shows some of the recent works that you have already done, and examples tab contains some of the examples that will guide you through the Colab the Colab environment. Then the Google Drive tab where you may see some of the Google Drive notebooks, some of the notebooks that you have saved into your Google Drive. And the GitHub tab, this can be used to find or search over some GitHub repositories and open those notebooks directly into our Colab. For example, once I type the link or type the URL of a user or GitHub user, we may see that there will be a list of repositories that will be using by him. So here we may see I took a repository called one of my repositories. Then you could see that here these are the notebooks that have been saved under this repository. So we may change the branch if it's available, and also we may select any of them and start in the collaborate. Then we can also upload a notebook file from our system using an upload function. So let's start. Okay, this is how a Colab notebook looks like. So here we can start a new notebook just by typing the new notebook in the file section, and it's loading. Okay, this is how a new notebook looks like. So first we can rename the notebook as notebook 1. Okay, now the most important part of the notebook is it contains 2 types of cells, a code cell and a text cell. In the code cell, we may type or we may execute any of the Python commands, just like okay. This is how it works, and we may see that it's running on a Python Google Compute Engine, and it supports Python 3 and Python 2.7. Also, we may see that the CPU version of the Colab supports about 12 GB of RAM and 107 GB of disk space, which is pretty enough for any of the projects. So we may explore to some other functions, like we may create a new notebook using the new notebook function in the file. We can open a new notebook either from GitHub or your drive or from your computer. Can also rename, save it to the drive, GitHub, or you may even explore through the history and make changes that you have already been made. And finally, if you need to download the notebook, then you may also use a download the option either as a notebook file or as a Python source code. And in the notebook settings is something where we may choose between the hardware accelerator. The hardware accelerator may be GPU, TPU, or CPU. If we choose it to be none, then it will be CPU. If we use the other two, then it will be either of GPU or TPU. And just like I have introduced code cell, there is another cell called text cell. Text cell is similar to like a text interface. We can use the features to bring some text outputs. So this is very useful because when we need to make reports or tutorials out of Python or for some of your projects, then you may easily use them for doing so, by which it will be easier to understand, to document, and also for your viewers to understand what the code is meant to or what we will be doing. So there are some other options like runtime, where you may interrupt the execution. Sometimes you might have made some mistakes like entered into a infinite loops, or sometimes there will be a situation when you need to interrupt the execution, then you can use interrupt execution, and times when you need to clear all the existing assignments, then you can use restart runtime or factory reset runtime, and it provides a lot of functions that is useful for a programmer. And here you may see that, just as I said, when you use these text cells along with the code cell, you may see that each of your headings will be formed into a new section where you can make something like a textbook where the contents will be listed in the left side and your work will be in the right side. So that was an introduction to the Colab. So we will move on into a detailed steps and detailed works. In the second section, we will be looking into how to collaborate your works with your team or your companions. So there are three ways in which you could share this with your team. First thing is by the conventional method called GitHub. Through GitHub, you may commit your work and enable any of your coworkers or the team members to access the work over the Colab. And the second option is to share it over the drive. You may save the work notebooks into your Google Drive, and you can share a file with any of your members so that they may directly access them. Then the third option is by using the share Colab notebook option in your Colab environment. So when you're using your GitHub for sharing, first you should commit or save the notebooks into your GitHubs. so that you can help others or you may enable others to access the notebooks through Google Colab. You can also access the notebooks in the Google Colab using a customized link like collab.research.google.com/github/ the name of the organization or the owner of the repo followed by the repository name, which will lead you directly into that particular notebook in the particular owners or organization's repository. Also, you may open a file from the GitHub using Open Notebook function in your file option and search for the repository in the provided area. And you can also improve your notebooks just by adding the following code snippet or the HTML snippet by which it will give an icon over your notebooks, by clicking over which you could directly open your notebooks in the Google Colab. So now let's dive into the most powerful tools that are provided by the Google Colab called GPUs and TPUs. Many of us know that Google Colab is providing free hours of GPUs and TPUs for our model or our ML models or deep learning models. But many of them don't know how to use these GPUs or TPUs in your model training. So having such a great power but don't know how to use it is a big issue that have been facing in these days. So moreover, the introduction of GPUs and TPUs has also introduced a great power for our developments. The concept of neural networks were introduced very earlier in the mid-90s, but it were used or come into application only around 2000s and these years, just because there wasn't such a huge computational power, but now we have these GPUs and TPUs for our model. So let's move on. Okay, this is how we will be using a GPU in our Colab. First of all, we should change our notebook settings. In notebook settings, we should change the hardware accelerator to GPU. After that, we should import the TensorFlow module in the Google Colab and get the device name. You may use this code snippet to get the device name in the environment, and you may train the model, or you may build the model and train the model under this code snippet called with tf.tensorflow.device, and within this brackets you will be giving a device name by which you will be enabling that section of code under this snippet will be running on your GPU instance. And very similarly, we will be using our TPU. When we are using the TPU, we should first set our hardware accelerator settings in notebook settings to TPU, and then we should import the TensorFlow module. Then we should get the TPU object from the TPU cluster resolver API, and after that we should configure the TPU, and we may bring the scope using the snippet with TPU strategy.scope. So any of the models that were trained under this code snippet will be running or training in the TPU instance. The GPUs and TPUs are having very much power over the CPU, which helps you to model or train your models much faster and giving you more power in your developments. Now let's see how to run your model and train your model over CPU, GPU, and TPU, and how different or how faster the executions will be. So this is a Google Colab notebook that I have created to experiment it with CPU, GPU, and TPU. So first of all, we will see how different that each of them will be on training. So the first step will be setting the notebook settings to GPU and running the import sections and initialization section. So the first thing that I would like to remind you is that all these encodes are run over the TensorFlow 2. TensorFlow version in and above to version 2. So first we will be importing the modules and initializing the GPU. Then we will be reading the data set from the fashion MNIST data from Keras datasets, and we will be creating a Keras model, and I have written it as a function so that I may call it multiple times, and then I have created separate functions for a model to train over CPU, then over GPU, and over TPU. So now we will be creating a model using the create model function, and you may see that once we run it over the CPU, it takes around 7,710 seconds for running 17 epochs. So while the same time the GPU takes around 133 seconds, that is just about 2 minutes. So you may see the difference when it comes from CPU to GPU. It's become around 35 times faster. So when it comes to TPU, it reduces the speed to 27 seconds. So when you run into with TPUs, you should change the hardware accelerator from GPU to TPU, and while you change the hardware accelerator, your runtime will automatically be reset. So you should run these code cells once again, and create the model. Then we may see how the model runs over the TPU. It takes some time because it takes some time for initialization of the TPU. Here you may see that the TPU is located over this address, and 8 cores of TPU, which will be highly useful to know when you will be modeling or processing it over batches. So you may see how fast it is in training, and yes, it's finished, and it took just 25 seconds. That is even less than half a minute, whereas even a TPU model took around 2 minutes. So you could guess how fast it is and how useful it is over modeling this deep learning use cases. So here I have this the code that I have used to initialize the GPU, and this is how the GPU model has been trained, or the entire training process comes under the scope of this code snippet. And in case of TPU, this will be the here we will take the TPU here we will take the TPU object, then initialize it, then finally the entire process of running will be under the scope of TPU. So this is how you will be training GPUs and you will be training models using GPUs and TPUs. So as the next part, we will see how to take models inputs from take data inputs from cloud buckets, BigQuery, and of course how to authenticate with your drive. In this fourth section, we will be detailing about preparing the data for your ML model. So in this section, we will come across how to access your data from several sources like GitHub, to use it from your Google Drive using your cloud bucket, and how to access using BigQuery. BigQuery is one such a big tool which can be used in data warehousing and processing great data which contains millions of rows and GBs of data. So while preparing your data, the most important feature that Colab provides you is you have a Linux or Unix-like interface where you may download any data using your shell commands like wget or curl or anything like that. And you are also provided with features of cloning your data from GitHub. You may push and pull it anytime and enjoy all those powerful tools that are provided by Linux. And Google Colab also provides its power just by enabling you to integrate your model with data from your Google Drive, Google Cloud Bucket, or from the BigQuery and from much more sources. So let's start. Now, first of all, we will begin with how to connect with your Google Drive. We all know Google Drive is a free source where you may store your data and access them. So by using the following code snippet, you may authenticate your Google Drive with your Colab notebook. So here we will be authenticating by importing the drive method from Google Colab module, and we will be mounting it on a path called content drive. Then once we run this code cell, an authentication link will be generated. Once we click on the link, it will be redirected into a login page where you will log in with your Gmail account and give access for Colab to access your Google Drive data. And once you are given the permissions, you will be getting a verification code, and you should paste it back on your Google Colab notebook. And you will be now now you have integrated your Google Drive with your Colab notebook. So now you may explore through your Google Drive just by using the Linux commands like cd, ls, and all. So now another important feature or another important tool that we have is using Google Cloud Buckets. While training the data over TPUs and GPUs, Google Cloud Bucket is always a better alternative to store your data, though it's not free. It has great features of scaling and data management, and we may integrate the Google Cloud Bucket data to our ML model using Google Colab. For that, first of all, we should give the permissions to the Google Cloud Bucket so that it may be accessed publicly. And second step, we may access the data from the Google Cloud Buckets by either using the TensorFlow dataset module, or by using TensorFlow IO module, or by using the gsutil tool provided by the Google Cloud. By using gsutil, you may authenticate your Cloud Bucket with your Colab notebook, and you may access the data just like you access it from your Linux commands. So when you are using TensorFlow datasets module, you may use TensorFlow datasets.load method, by which you may load the particular data from your Google Cloud Bucket. The below snippet shows how it works. Here, the dataset train and the test variables are initialized with train and test dataset of MNIST respectively from your Google Cloud Bucket. While using TensorFlow datasets.load method, the name variable will be given with the name of your dataset, and the split variable will be assigned with the names given for your train and test splits. And if it's not there, you may avoid this. And your Google Cloud Bucket address must be given to the data directory variable. And finally, we may use the TensorFlow's input-output module to access the data from your Google Cloud, where you will be giving the link or the address of your data location in your Google Cloud Bucket, and it will be read using the glow function provided in the TensorFlow IO module. Now, BigQuery is a large warehouse management system where you can run queries over millions of rows of data, and you may even handle GBs or TBs of data set efficiently and effectively using BigQuery. BigQuery is highly scalable and can be used for any range of data sets. So before using the BigQuery in your Google Colab, first of all, you should have a project ID from your Google Cloud Console. If you don't have a project ID yet, just go and create one and get the ID. It's free. And once you have the project ID, you must use it in the Google Colab to access your BigQuery processing. You can process and load your data from BigQuery using three methods. The first one is using Pandas input IO module, and the second one will be using the BigQuery API provided by the Google Colab, and finally using the BigQuery Magic functionality provided by the Google Colab. So now let's see how it works. Let's start with authenticating with the Google Drive. For authenticating the Google Drive, this code snippet is used so that the Google Drive will be mounted in the location provided as content drive. While we run this code cell, we will be getting a authentication URL. Once we click in the URL, we will be redirected into a sign-in location where we should sign in using our Gmail account. Then we should provide the permissions. Then copy this code and paste it in your provided location in your Google Colab. You will get an output like this that's mounted over the given location. So once it's mounted, you may access the drive as your own local memory, and you may use your Linux commands to access and optimize them. So the next option we have is using the Google Cloud buckets. Here I am importing the TensorFlow module and is directly giving the location of the cloud bucket. So I will be loading the data using the TensorFlow IO module and the glob method, and here we have the dataset in the file names. Now, BigQuery is another alternative option which can be used when you need to process large set of data and which contains millions of data to be processed. So the first thing you should need is you should have a project ID. A project ID may be created just by creating a new project in your Google Cloud Console. Once you have created it, you may copy the project ID for working with BigQuery. So the first method we will be using is from using Pandas IO module. Using Pandas IO, we may read or we may execute the BigQuery just like this. The highlighted part is a BigQuery, and here we will be giving the first attribute as the query, then project ID, and finally the dialect. And this will read the output into the df or data frame variable, and this df.head method will give you the first 5 outputs or the first 5 rows in the data frame. Now, in order to use your Google Cloud BigQuery API, you must first authenticate it with the Google Cloud using this code snippet, and using Google Cloud BigQuery API, you may create a client using the project ID, and you may run the query here. And we will be using the toDataFrame method to convert it into a data frame. Once the execution is finished, here you have seen that such a large set of rows has been processed very fastly, and the first 5 set of rows are shown here, and it contains too much columns and around this much rows. And the next option we will be having to run your BigQuery is using BigQuery Magics in the provided by Google Colab. The BigQuery Magics is usually represented using 2% characters, and the project ID will be given as this, and the output of the query will be saved into the DF data frame. Here the query will count the entire number of rows in this data set. So the output will be this. So here is another example where we will be reading all the columns in all the columns in the first 100 rows. So once we execute the query, we will get the output like this in the data frame. So that's how this works, and now we will move on to that deep learning use case. Now it's time to apply what we have learned through this section. So in this 5th section, I will be showing a deep learning use case of classification of flower images. So I will introduce you a concept of machine learning pipeline. A machine learning pipeline is a series of process or a process in which a ML model evolves. Thus, the first step of the machine learning pipelining, it is the preparation of data. The data from different sources are prepared in such a way that it can be used as an input to the model. So it always needs some sort of cleaning, anomaly detection, and sometimes reformatting. And the next process or next step in the machine learning pipeline is building the model. While building the model, we will select or choose upon what kind of algorithms we need to use, and the layers we need to implement, and the parameters and all. And once we have built the model, we will train the model over the data. During training, we can train our model over TPU so that it will be fast and we will be getting good results in a short period of time. And the next step after we training the model is testing the model over a test data. While we testing, we can know that how much the model we have trained is accurate or can be used for real-world applications. Once it's tested successfully and evaluated, we can deploy it for user input. So a good and a powerful model doesn't end with the deployment. It usually learns from the new set of data it's getting, and the process goes on and on in a cyclic fashion. So it's time to get into the code. Here in the first section, I have imported the modules that were needed to run this model. And here I have initialized a TPU cluster and created a scope. Here we may see that the initialization steps over the TPU address and over 8 cores of TPU. Here we will be using the concept of cores of TPU while batching the data. Now, during preparing the data, we are getting the data set from the Google Cloud bucket of a flower database, where we will be getting images of different kinds of flowers. Now we are batching the data set with a multiple of 16 with the TPU strategy, the replicas, where the output of this TPU strategy replicas will be the number of cores in the TPU. So the number of cores in TPU usually plays an important role in deciding or batching the data set. Now the data set is split into test, train, and validation data sets so that we may train the model, validate, and test it on an isolated data set. And now these steps involves processing the data for the model input. And once we have processed and loaded the data set, we may use it for training. And these are the classes or the labels of the flower images that we will be using in this dataset. Now we will be creating a model using the Keras models from the TensorFlow, and we will be compiling it using an Atom optimizer and a categorical cross entropy loss. The categorical cross entropy because this will be a classification model. Now we will be creating the model under the scope of TPU, and the model.summary method will give the details about the model, that is the architectures used, then the number of parameters trained, and the shape of the output. So this shows the layer or model type, then the output shape, and the number of parameters over which it is trained. And the next step in the machine learning pipelining is setting the parameters. While we training the model, setting the parameters is also an important role, because setting the change in parameters may give different results over each training. So here we are training the model for 12 epochs with 23 steps over each epoch, and we are giving the starting learning rate to be small and the maximum learning rate to be this multiplied by the number of cores in the TPU. And here we will be creating a function to calculate the best learning rate over each iteration, and this learning rate will be optimized with the Keras learning rate scheduler, and it will be stored as a list in the learning rate called by list variable. Now it's time to fit our model with the training data set and validate with the validation data set. And we will be giving the input parameters as training steps and epochs and the calling rate. Now this will be trained under the TPU scope so that it will be run faster, and it gives an accuracy of around 0.9 99% of accuracy, and considerably less loss over the training dataset, and 96% of accuracy over the validation dataset. Now the history shows the output of the model, which gives metrics of accuracy, loss, and learning rate over each iterations. Now the final step after we creating the model is making the predictions. Making the predictions over a test module will tell us how accurate our model is and how good it is working. So we will be making the predictions by using the model.predict function, and the class labels and the predicted labels are saved into the class ID and prediction ID, so that we may compare it and plot it with the values, whether they are predicted correctly or incorrectly. Once we have plotted the outputs, we may obtain a result like this. In this, we can see that there are correct predictions and also incorrect predictions, where we can see that the roses are predicted incorrectly here, and here the sunflower is predicted incorrectly, and here the tulips are predicted incorrectly. So this model shows that it has some correct predictions as well as incorrect predictions. So it's always important to notice that we should always customize our model such a way that we will be obtaining a good result over the test dataset too. So what we will be doing for making much better predictions will be to adjust the training parameters, like increasing the number of epochs and increasing the number of training steps can be a useful measure to increase this test accuracy. So having a higher accuracy over the training dataset and the validation dataset doesn't mean your model works well over the real world dataset. So it's always important to have a test dataset which is always isolated from a training dataset. So now it's time for wrap up everything that we have learned so far. So through this session, we have learned and introduced a powerful tool called Google Colab, and we have learned how to prepare a working environment and collaborate and work in a team using the tool of Google Colab. And later we learned how to store the data in GitHub data directory, and how to access data from various sources like Google Cloud, Google Drive, using BigQuery, how to process a large warehouse of data and how to get the result as a data frame. Then we learned how to use BigQueries and Cloud buckets to process the data, and later we learned the power of GPUs and TPUs in the deep learning use cases. And finally, we implemented everything that we have learned into a machine learning use case of flower image classification. So that's all for this session, and it was good to meet you all, and thank you.